question was asked in GATE 1992, and the question states a priority encoder accepts three input signals. So there are three input signals A, B, and C, which the encoder accepts and produces a 2-bit output. So based on the combination of A, B, and C, we will get a 2-bit output. We will see how it will be corresponding to the highest priority active input signal. Assume A has the highest priority followed by B and C has the lowest priority. If none of the inputs are active, then the output should be 0, 0. So here it is saying that A should have the highest priority. So if A is 1, whatever others may be, it doesn't matter. A should be given the priority. And similarly, B has priority greater than C and less than A. So whatever C, B, if B is 1, then the priority should be on B. And if C is 1 and other are 0, C anyway has the least priority, so a code will be assigned to that. Now, how the code is assigned, we will see here. If none of the input are active, then the output should be 0, 0. Design a priority encoder using 4:1 mux. If the inputs are active, then it should be 0, 0. So if both all of them are switched off, that is 0, 0, and 0, then the output should be 0, 0. If C is 1, then we have assigned the output of 0, 1. If B is 1, then we have assigned the output of 1, 0. This is 1 basically, this is 2, and this is 3. So when A is 1, then this is 3. So for x0 and x1, we can write a truth table, and based on that we can get an expression. I have written the expression here directly because the circuit is very simple. Okay, so for x1, these two cases are 1 and 1. So here it is 1. So here, see this line, here it is 1. So here A is 1 and whatever B is, it doesn't matter. So we have written A plus, we can write B plus B bar times C plus C bar, and if we expand it, then that also can be done, but it is simpler this way. And here we have 1, so A is 0 and B is 1 and C is don't care. So we don't write the don't care because any value C maybe it doesn't really concerns us. So A bar B. Now we are writing for x naught. X naught is 1 for this case and this case. So x naught is 1 for this case. So A bar B bar C, A bar B bar C, plus in this case when it is A. So in both the cases we have got A. An interesting observation. So now we have to construct, look here, we have to construct a mux multiplexer, 4:1 multiplexer to get the output. So x naught and x1 should be derived from a multiplexer. So this is the multiplexers we got, and A and B are the select lines, and C we will feed in here, okay, on the input line. So for x1, we have written the statement here. X1 is this. So when it is A, then B or B bar, it doesn't really concern us. The input should be 1. So we have feed in 1 at the input. B, A bar B, then also it should be 1. And here A bar B bar is not there present. It is because it must have been multiplied by 0. That is why that term has vanished. So A bar B bar times 0. So we have feed in 0 here. When this is 0, 0, then this line is selected and we have feed in 0 here. When it is A bar B, then this line is selected and we have selected 1. And AB bar, then this line is selected, this is 1. And when AB, then this line is selected and this is also 1, which is derived from this expression. So now let's go to the second expression. In second expression, we have A bar B bar. So the first line, A bar B bar is the select line, right? So A bar B bar times C. So we will feed in C here. Now A is there. So for A B bar plus AB. So for both combination of B, we should be getting 1. So we have feed in 1 at third and fourth input, and for the second input we don't have an expression, that is A bar B we don't have, so it must have been multiplied by 0, and that is why we have multiplied 0 here. So the second input line is 0, and this completes the implementation for x2. So this is for x1 and this is for x2.